So far, we've looked at representing the atom and the electrons using the Bohr model. And with the Bohr model, we've looked at the total number of electrons. What we'll do with Lewis dot diagrams is looking only at the outer electrons or the valence electrons only. So keep in mind with our periodic table that we can look at the total number of electrons using the atomic number. So here's our atomic number in the upper left-hand corner of this one, and that will equal our total number of protons as well as our total number of electrons. The periodic table is also helpful because we can use it to tell us how many valence electrons there are. So the number of valence electrons will correspond with the family or the column. So our first family will have one valence electron. Our second family with beryllium and magnesium and etc. will have two. We'll skip our transition metals, and then we'll have 3, 4 for the carbon family, 5 for nitrogen, 6, 7. And then for our noble gases, helium will have 2 valence electrons, giving it a stable duet, and then the remainder will have 8 valence electrons, giving them a stable octet. A duet and an octet are important whenever we talk about bonding. So let's first talk about our noble gases, which are found in this column. Again, our duet is having 2 electrons in the outer shell or in the valence shell. And a duet, or an octet, is having 8 electrons in the outer shell. Elements that like to function with a stable duet are things like hydrogen, helium, lithium, and beryllium. Everything else will function with an octet, which means that they would like to have 8 electrons in the outer shell. If we look at the Bohr model for helium, we could see that it has 2 total electrons. So it has 2 total electrons, and it also has 2 valence electrons. This means that it has a duet, and it doesn't need to gain or lose any electrons in order to be considered stable. For neon, we could see that it has 10 total electrons, which is the same as protons, so it has 10 total electrons. And in terms of the outer shell, it has 2, 4, 6, 8, so it has 8 valence electrons. And this will give us an octet, which is also stable. It doesn't want to gain or lose any electrons. If we do a Lewis dot diagram, we'll do an example for neon. Neon, we put our chemical symbol in the middle, and then we put our electrons at the top, the sides, the bottom, and the other side. So we would go 1, 2, 3, 4, and then we'll go ahead and double up only when we need to. 5, 6, 7, 8. This shows us that neon has all of the electrons that it needs, and it doesn't want to bond with anything else. Now, let's take a look at a few more examples. So if we look here, we have sodium and potassium, which both come from our first family. Keep in mind we said that it has 1 valence electron, which is what we see here for our outermost electron. Okay? For sodium, we have 11 total electrons, but still 1 valence. And for potassium, we have 19 total electrons with 1 valence. For both of these, we're going to draw a Lewis diagram. And so we would put our chemical symbol in the middle and then 1 electron to represent the valence electron around the outside. This shows that sodium and potassium would both like to lose 1 electron. So if it loses 1 electron, that then means that it has 8, or an octet, in its outer shell. Same thing will be true of potassium. It will have an octet. Now, let's take a look at phosphorus. Phosphorus is here. It's in the nitrogen family, which will have 5 valence electrons. So let's check it out. We could see that phosphorus is atomic number 15, so it has 15 total electrons, and then it has 2, 3, 4, 5 valence electrons. In order to draw our Lewis dot diagram, we'll put phosphorus symbol in the middle, and then we'll put our valence electrons. So I will go 1, 2, 3, 4, and then only double up whenever I need to. Whenever we look at phosphorus, we can see that this electron could use a buddy. And so that tells us that phosphorus would like to either gain 3 electrons to get a stable octet or share 3 electrons to get a stable octet.